The local density approximation has been applied to many systems, so we do have a lot of information on the performance of the LDA approximation to have different properties of the systems, of atoms, molecules, solids. And here we are going to have a general description on the performance of this LDA in order to have a general picture of how well it does in order to analyze different properties. And actually, the key feature for the success of the LDA in order to analyze different properties is in this square here. The accuracy of the LDA for the exchange energy is typically within 10%. So we have a 10% error for the exchange energy, and the exchange energy you are getting within the LDA is actually smaller than the exact one. While the normally much smaller correlation energy is generally overestimated by up to a factor of 2. So we usually have an error in the correlation energy of 100%, and it's higher. And this is the interesting thing here. The two errors typically cancel partially, and that's the partial reason of the success of the LDA. But we are going to see different features, different properties, and see how the LDA is doing to analyze these different features, because the success, of course, the LDA is not the same for analyzing all the properties. So first, structural, elastic, and vibrational properties are often good enough. So, for example, the crystal bulk lattice constants are accurate to within 3% and usually are underestimated. So that means that the bond length, for example, lattice constants calculated within the LDA have an error of 3% approximately compared to the experimental one, and usually they are smaller. And actually, if they are smaller, the forces that the atoms can see when they are separated a little bit from these equilibrium positions are expected to be higher. And that's why usually the bulk moduli is somewhat too large, the one calculated within the LDA. And it's not uncommon to see that the error might be higher than 10%, especially for D metals. And also because of that, because you expect that when the atoms separate from this equilibrium position, you expect to have higher forces between the atoms, because lattice constant bond lengths are usually smaller within the LDA than with the experimental one. Phonons calculated within the LDA are somewhat too stiff sometimes. Okay. About the binding energies, the binding energies calculated within the LDA are too negative. That's what's called overbinding. And the difference or the error is about several electron volts. For example, because of that, typical errors of dissociation of molecules or cohesive energies, it's around between 10 to 20%. So it's not good enough in order to describe that binding energies, like cohesive energies of dissociation of molecules. And related to that, the activation energies in chemical reactions is unreliable. They are usually too small or even absent. So that's what happens, for example, in hydrogen on various surfaces like aluminum, copper, or silicon. The relative stability of crystal bulk phases can be sometimes uncertain. So you know that changing pressure or temperature, you can have a phase transition from one structure to the other. And actually, you can analyze this phase transition calculating the energies for different structures, and that the one having the lowest energy, the lowest enthalpy, depending on what kind of transition you are analyzing, is the one expected to have to occur in the experiment. But these transitions or this relative stability or the energy difference between these different phases sometimes so small that the calculations that are done within the LDA is not accurate enough in order to have a good relative stability for these crystal bulk phases. For example, the high pressure phase for silica is more stable within the LDA than the one that happens experimentally at zero pressure. Related to that, sometimes the transition pressure, which is calculated when you have a phase transition under pressure, is underestimated. So again, if you apply a pressure, you can have a phase transition from one structure to the other, and the pressure where you do have this, or you expect to have this transition, is called the transition pressure. So the calculated transition pressure compared with experimental one is usually underestimated. For example, that's what happens in silicon and germanium, where you do have under pressure a phase transition from a diamond structure to a beta-tin structure, and the transition pressure where this transition occurs, even though the transition is predicted with the calculation, the transition pressure it's underestimated. The one calculated within the LDA is underestimated. The electronic structure which is calculated within the LDA can be usefully interpreted in the sense that the density of states and the band structure you're getting within the LDA it's quite nicely comparable with the experimental one, except the band gaps, because the band gaps you have for even semiconductors or solids or insulators are usually too small, so the band gaps are not well described within the LDA. The LDA can also fail in systems where, like heavy fermions, they're so dominated by electron-electron interaction effects. For example, so the LDA doesn't work in these externally correlated systems. And actually, the LDA does not include van der Waals forces. Van der Waals forces are not reproduced within the LDA approximation. So in systems where they are stable because of these van der Waals forces, like for example, these rare gas solids, you don't expect them to be well described within the LDA. So these are basically the main features or the performance and different features and different physical properties within the LDA, which can be useful in order to have a general picture in order to see how well the LDA is doing in order to analyze different physical properties. As you can see, okay, the LDA is doing quite well in order to analyze physical property in quite many different systems. However, it also fails in order to analyze other properties. And also, it's interesting to characterize and the different the magnitude of the errors that you can obtain within the LDA.